these guys came to me and said, we love each other, we would like to be a team, and we be a team. And I said, well, who's the team? Yeah, you can be a team. Okay, what do you want to do? Well, we want to do a pedestrian bridge. Where do you want to do a pedestrian? Well, we'll make up one, somewhere in the south side. No, one bar to another over Carson. Okay, that's what you want to do, that's okay with me. And suddenly, somebody from Hollow Oak Trust contacted somebody here and said that we would like some help with preliminary engineering on a hiking biking trail bridge. And I went to these guys and said, we have this inquiry, are you interested? They got in touch. Bing, bing, bing. Suddenly we end up with a project, a real project. A project that's going to be built eventually. And we're hoping that the work they've done is going to help make a decision, help get funding for this project. And I'm not going to say more about it because they got a whole lot to say. You're up.
Good morning. I finally get to say that I'm a part of a group that's sold out. We are 29.9 in engineering, and our project was to develop a pedestrian bridge for Hollow Oak Land Trust. I am project manager, and my name is Jonathan Miller.
My name is Steve Dunn, and I'm part of the geotechnical team.
Dean Lewis, I'm also part of the geotechnical team.
My name is Dustin Volsky, also part of the geotechnical team.
Keith Dougal, I'm on the structural team.
Hannah Furneaux, I'm also on the structural team.
And I'm Jonathan Kelly, also on the structural team.
Hollow Oak Land Trust is a nonprofit organization that owns 400 acres. They are based out near the Pittsburgh International Airport in Moon Township, Pennsylvania. They have a 260-acre plot in Moon that is Montour Woods. And our project was to create a bridge that would cross Montour Trail. Their vision is so that they can connect their 10 miles of trails to the Montour Trail. That way, with hope that people that are either on their trails then have access to the Montour Trail, or so that people that are on the Montour Trail then have access to visit their wonderful conservation area.
All right. As John just said, our bridge is intended to connect the Hollow Oak Trail system to the Montour Trail. Our bridge is designed for bikes and pedestrian traffic to encourage kind of cross-use between the two systems. When we first went on site, our client had told us that the plan for the bridge was about an 80-foot long bridge. Upon further review, though, we found a sewage line in the west abutment, or west bank, that had to be crossed over because they have a 10-foot easement on either side of that sewage line. So we ended up with approximately a 110-foot span for our bridge. We also know that there is a gas line somewhere on the east side of where our bridge is. It won't affect our actual bridge structure, but needs to be considered in the design and construction of our approach ramps. This bridge also spans between Moon and Robinson townships, so we had to consider the wishes of both townships and figure out who is ultimately going to be permitting this bridge. So here's some pictures that we took while we were on site. The west embankment, as I had just mentioned, is the one with the sewage line, and the east embankment is the one with the gas line. When we went out on site, we conducted a survey and found that the bank-to-bank distance is approximately 77 feet, and each of the banks are about 5 feet tall off the stream bed. This is a picture of some of the points that we collected while we completed our site survey. We focused predominantly along the length of the bridge and the approach ramp that's connecting into the Hollow Oak Trail system. So our benchmark 1 was the first point that we took. We used an arbitrary points for that benchmark because we didn't have any reference values in the area. This being said, if we got a reference value that we could survey, we could then take that back to the point and create actual elevations for all of our survey points. So the TP25, which is at the top of the screen, is in the center of Hollow Oaks Trail that we are connecting to. As you can see, we also took some points along the stream bed so that we could then input them into a hydrologic analysis.
So when you're designing any kind of a structure over top of a river, that structure has the potential to cause impacts on the water flow. Specifically, according to the government, we need to check for whether or not it will raise the water level. So the government restricts how high the water level can change, and specifically, according to FEMA, our site is limited to a 1 foot increase in water surface elevation because it is a non-detailed study area. So in order to satisfy this requirement, as well as to determine how high the bridge would actually need to be built and the forces of the water on the abutments, we put the stream survey information into a hydraulic model using a program that was developed by the U.S. Army Corps of Engineers. We found that the minimum height of the bridge over the water was 6.78 feet. So we designed our bridge to be an even 7 feet above the water during a 100-year flood. We then found that the maximum velocity of water that would be hitting the abutments ended up being about 2.4 feet per second, which translated into about 72 pounds of force. Finally, we determined that with the addition of the bridge, the max water surface elevation at any point along the stream was raised by 0.9 feet. This is under the 1 foot limitation set by FEMA. Therefore, we were able to move ahead with our analysis and with our design.
So to begin with our structural design, we decided that we were going to do 3 complete designs using 3 different materials. We decided to use timber, fiber-reinforced polymers, and a steel structure. To begin with, we needed to determine what our loadings were going to be. And to do this, we used the AASHTO LRFD guide specifications for the design of pedestrian bridges. And that dictates that we have a 90 pound per square foot loading. And the pictures you see on the screen come from an AASHTO study that demonstrates what these different loading conditions look like. And when you factor the 90 pound loading, it ends up being approximately what the 150 pound per square foot loading is, which, as you can see by the crowding on that shot, that's a very unlikely condition to ever occur on our bridge. And we also decided of the loadings we needed to consider, we only needed to consider the live, dead, wind, and water loads. Per our client's request, and because vehicles aren't allowed on either of the trail systems we're connecting, we didn't have to design for a vehicular load at all. So our preliminary designs, we decided to investigate 3 different truss types. We did the Pratt truss, the Howe truss, and the Warren truss. And for each of the 3 materials we're designing in, we decided to go with the Pratt truss for various reasons that will be discussed later. Our first alternative that we investigated was fiber-reinforced polymers, or FRP. And the reason we went with the Pratt truss for this design was because we wanted to get as many members out of compression as we could, especially the diagonals because they're the longest members, and we started to run into buckling issues with those. So for this design, we have a 5.5 foot high pony truss because we didn't gain much efficiency from making it a higher truss because the long, slender members became a buckling issue with that. So to begin with, we should probably talk a little bit about what fiber-reinforced polymers are because it's not a standard building material. And it's a composite material that's made out of resin and glass fibers. And the resin's typically a polyester or vinyl resin, and the glass fibers make up between about 45 to 75% of the total weight of the structural shapes. And the process is shown here on the right of how they make it, where you basically have to combine the resins and the glass fibers, and it's pushed through the preformer, and then as it goes through there, it's heated and it begins to cure. And then you pull it through the die, and then you cut it off at the cutoff saw as part of a continuous pultruding process. And for this bridge, we decided to use the Creative Pultrusions Pultex 1500 series. It is the lowest of their 3 grades, and as such, it's the least costly. For the higher grades, you gain a little bit of strength in some of them, but you also gain qualities like fire retardant characteristics and also chemical resistance. But for a bridge like this, we didn't think those were necessary because they will not face those conditions as you're not really going to cross a bridge that's on fire and shouldn't be any chemicals going on the bridge. So why did we choose FRP? The main reason we chose it is it's a much lighter weight material, and we thought we could make it easier to construct if we built with a lightweight material. In comparison to the timber structure, it weighs about 30,000 pounds less overall just for the truss, and compared to the steel, it's about 10,000 pounds lighter than that. And also, some of them, the structures with FRP have an ease of assembly. They're essentially shipped as an erector set, where you just get the pieces ready to go and you just bolt them together and put them in place. And also, there are lower life cycle costs. And there's also, because there's very little maintenance involved with the FRP shapes, and there's less embodied energy than either steel or aluminum, which is another alternative that we didn't consider. So that might be something that's of interest to a group that's involved with conservation. There are drawbacks to using FRP, though. The first being that there's no real code for designing with this. So we had to use what's pictured here on the right. It's the pre-standard for LRFD of FRP structures. It's for ASCE. And that was all we had to go on, so that's what we had to use. And it's a relatively unknown material behavior in the sense that timber and steel are both well known and have been studied for many years. So the result of this is that we have very conservative design equations. So that made it a bit challenging. And the connections were another big issue we had, and again, that's largely because of the conservative nature of all the equations. And the final and probably most major drawback is it's significantly more expensive than designing with the other materials that we considered. So when we first started designing our truss members for the FRP design, we realized quickly that the compression members are going to control the design due to our equations. The basic equation is shown there, which is just saying the ultimate strength has to be, or the ultimate force has to be less than our nominal force, and also 70% of the theoretical using the nominal compressive strength, which is 33 KSI for the shapes that we used. And we first started investigating W shapes, just standard structural members. But we found that as we increased the size to deal with our 123 kip loading, we were actually losing strength because we had issues with local flange buckling as the flanges started to get wider. So we had to abandon that shape, and we eventually came to use 4 inch by 4 inch by 1/4 inch thick box sections. And to get the strength that we needed, we had to combine 4 of them into a built-up section. And those built-up sections are going to have to be bonded in the factory so that we ensure that we get a good bond and we don't have any errors in the field by trying to piece them together out in the unknown environment. And that's what we'll use for our top chords and also our end diagonals. And for the vertical members, they only face like about a 14 kip force. So we initially had those designed as 4 inch equal leg angles. But once we got to designing the connections, they started failing there because of the conservative equations. So we had to go back to built up sections for those too. However, those are only going to require 2 of the 4 inch boxes instead of the 4 like we have for the top chords. Tension members was largely similar. Again, we have the same factors. It's a slightly different phi factor. And the lambda in the equations is the time effect factor, which is equal to 0.8 because the material will lose strength over time, over its lifespan. And we had lower loads in this. The ultimate load is about 120 kips on our lower chords. So we eventually decided that we would, again, use the same members that we used for the top chords, the 4 inch by 4 inch boxes, built up sections. And we had to check both the gross section area of our composite shapes, and we also had to check the net section once we subtracted the area for the holes that we would have to drill to bolt our sections together. And finally, we had to design our connections. And as you see, again, we have the same lambda factor. The phi factor varied depending on which design check we were making. And then we also have the C factors, which are the condition factors. The first is the C delta is the geometry factor, and as long as we follow the code in the pre-standard and meet all the requirements, that's just 1, so we don't have to worry about that. The CM is the moisture condition factor, which had a value of 0.85, and that comes directly from a table. And CT is the temperature design factor, which comes from an equation in the standard, which is designed so that anything below 90 degrees is equal to 1, and anything above has a linear relationship to its strength. And that's because as the temperature increases, the resin loses its strength. So the higher temperature you go, the lower the strength of the material. And we used the design temperature of 125 degrees Fahrenheit, as we thought that was a reasonable approximation of what it would face in the field on a summer day in the sun. And that ended up giving us a factor of 0.7. And when you combine all of those factors together, we're already designing at approximately 48% of the strength that we started with before we used those factors. Another thing we were limited to was the pre-standard only allows for 3 bolt holes, as you can see in the illustration of a connection idea there. So we couldn't add strength by going longer and more bolt holes. And one final thing we had to do for the connections is the hollow sections inside the 4 inch blocks will have to be filled with a material, which we decided to use wood blocks for that. And there are two reasons for that. The first is that we don't want it to get the FRP shapes to get crushed by over-tightening of the bolts. And the bolts themselves will only be in the snug tightened condition, which is analogous to just how the lug nuts are on the wheel of a car. And the second reason is there will be bolt flexure in the middle if it has forces applied to it. And if you have that in the middle, the bolt won't be able to flex, because if that happened, we would lose about 50% of our capacity in our bearing strength condition. And now I will turn it over to Jonathan to talk about the steel design.
So as with the FRP and the timber trusses, we decided to go with a Pratt truss design for this steel design. And you can see that on the screen. We decided to have the same members across the top and on the diagonal members, or the outside diagonal members. That way you don't see any changes in member sizes, which would potentially make the people using the bridge feel a little uncomfortable. Additionally, we have the bottom chords, all the same member, and the diagonals and vertical members inside the truss are also the same members. However, those are 3 distinct sizes for the total truss. So when we were choosing our members, we originally looked at using I-beams for all of the members, and we determined that the I-beams were incredibly over-designed. They ended up being able to carry somewhere around 2 times the force that they needed to. This made for a very heavy bridge, and so in order to try to reduce the weight, we started to look at the structural tubes and the double angles. Comparing those two, we found that they had about the same cost, so we needed to use some other design criteria to determine whether we were going to design with the double angles or with the structural tubes. So we looked at the connections, and with the structural tubing, the connections really need to be welded connections, whereas with the double angles, they can be bolted connections. Since bolts are generally easier to assemble, especially out in the field, we decided to go with the double angles for our main members. The next thing with the steel design we needed to look at was the wind load. There does not end up being a very large force, but it is still something that needs to be designed for. So we decided to go with a truss across the top. We originally were going to make it a tension-only truss, so that only members carrying tension were used in the diagonals. However, this proved to be infeasible at the connections, so we later changed our design to make single diagonal members instead of doubles, so that they would be able to carry both tension and compression and make the connections a whole lot easier at the nodes. So again, the cords in this are the same cords that were used in the vertical trusses. For the ones shown, they are both sides of the cords are the same. And then the diagonals end up using single angles instead of double angles, and we are using I-beams for the horizontal members. These horizontal members for the truss at the bottom of the bridge will also be carrying the deck load, so we decided to go with the W shape since they're capable of carrying a greater flexural load. Next, we still had to determine or design the moment resistance. Having a truss on the top is good, but it still doesn't keep the bridge from falling over. It just spreads the load out so that it goes to the outside of the bridge. So we had to design some kind of a moment frame, and we were using a K-braced frame as shown here, so that we can have simple pin connections at all of the nodes of the K-brace rather than having to design a more complicated moment connection at the corners of the truss. There will be 2 of these K-braced frames, one at each end of the bridge, just as you're entering the enclosed area of the bridge, and they will transfer the load down from the top of the bridge down to the bottom, and will then be transferred out to the abutments. So finally, with looking at steel, you have advantages and disadvantages, just like with timber and with FRP. On the advantage side, we have that steel has very high strength and very high flexibility, meaning that should there be some kind of unexpected emergency event, some kind of impact to the bridge will actually end up being stronger during the impacting load, and the bridge will deform and deflect rather than breaking. allowing anyone who might be on the bridge at the time to be able to have enough time to get off of the bridge. Second, the steel has a very low profile. It's very strong for the amount of volume and the amount of area that it takes up. So when you look at a steel bridge, it looks like the members are a lot thinner, allowing more space to be able to look at the area around you and having less of a visual impact on the surrounding area. Third, steel is a very familiar material. As was said before, it's been around for well over 100 years, and we know how it works, and more importantly, the contractors know how to construct it and how to work with it to put it together. So when you are building a steel bridge, the costs of erection end up being a lot lower than you might have with the wood or with the FRP, especially with the FRP because we don't really know much about it. Fourth thing is that the steel design does allow for both welded connections and for bolted connections. We're not using any welded connections in this design, but should there be a need to, it has that availability, whereas with the FRP and with the wood, you can't really weld the two together. And finally, the final advantage is that steel is a very inexpensive material, running somewhere around 50 cents per pound for structural steel. So compared to the wood bridge, it ends up being around 20,000, or sorry, compared to the FRP bridge, it ends up being $10,000 or $20,000 cheaper for just the materials than you would have for the steel. There are some drawbacks to using steel. The first is that it is a pretty low sustainability material. The plastic in the FRP is more sustainable, as proven by the suppliers, and the wood, it's wood, you can regrow trees, so it's clearly much more sustainable to use the wood than the steel. And the second drawback for using steel is that it has corrosion, and this is a concern not just for our bridge, but all over the city and indeed all over the world. And this is something that environmentally we have to consider. So we looked at originally using weathering steel, thinking, if the weathering steel doesn't really corrode, you don't lose a substantial amount of section, then it'll maintain the same strength. However, at the beginning when you first put it in, the weathering steel does still corrode and rust will end up falling into the stream, which is generally a bad thing. But secondly, and more importantly, we found that according to a study done by West Virginia University, when you put a wooden deck board on to weathering steel, there are very negative effects for the environment, at which point we decided to not use weathering steel, figuring we need to just not bring any problems in with the environmental side. So we decided then to go with the galvanization process for steel and have all of the structural steel be galvanized. This has low maintenance costs throughout the life of the bridge as compared to using some kind of a paint system. Considering that our client is trying to get money through a grant, we can't be certain that they will continue to have money to be able to continue with the upkeep of a paint system. So we need something that'll last much longer, and so we went with galvanization. So now we're going to hand it off for our wood design.
So our third choice was to go with timber, and just as in with just the FRP design, we chose to go with a Pratt truss because we wanted to keep all the diagonals in tension so that we did not have to deal with buckling, because the higher we got, the worse the buckling issues got. The lateral force carrying members just in our timber design are horizontal cords that connect the top and bottom truss and diagonals that go between the horizontal cords. So timber is it's a unique material that needs to be looked at with what is available in your area. And so we started to call sawmills, and we found out that two of the species in the western Pennsylvania area that we can deal with were oak and actually hickory. And so we went into the national design specification and that is where we got our selection from for the allowable stresses, because the allowable stresses change according to the species that you are using. And using Western Pennsylvania species, it also just allowed us to keep the cost lower, because it would be very expensive to ship timbers in from actually other parts of the world or the country. So when we talked to the sawmills, we were curious about the dimensions, because when you go to Lowe's or Home Depot and you buy a 2x4, a 2x4 is really not a 2x4, it's a 1.5 by actually 3.5. And we wanted to make sure that the dimensions that we were using would be dimensions that could be cut at a sawmill. And we decided to stay with rough cut lumber, so that whenever we dictated a 10 by 10, it would stay at a 10 by 10. And so the other concerns that when you go into timber design that you have to think about is the moisture content, because moisture content in timber is what really is actually one of the major factors that actually dictates the strength. And moisture content, as it decreases, actually strengthens the timber. And depending on the environment that you put your timber structure in, will dictate what the equilibrium moisture content that structure is going to achieve. And it's an assumption on our parts that we have to make. So knowing that our timber structure was going to be outside, we then dictated that the moisture content was going to be greater than 19%. And the reason why we choose 19% is the National Design Specification dictates that that your reference design values have to change if it's over 19%. As soon as you drop below 19%, then you're able to use 1, and you are not adjusting your design values actually according to the just according to the actual moisture content. And moisture content has one final thing that is a major concern, and that is the shrinkage and the expansion. Because as the timbers either absorb moisture or just evaporates the moisture, it will shrink or it will expand. The expansion is when it absorbs moisture, and it shrinks whenever it just evaporates the moisture out. And the major shrinkage and the expansion is caused perpendicular to the grains of the wood itself. And I will discuss this further whenever we get into connections, because that's when it becomes a major concern. So at this point in time, I want to go into the members and the connections. And as I talked, we try to leave as many of our members in tension. That way we do not have to deal with the buckling. Because once you go into compression, the buckling becomes a major issue. We have to use actually Euler's buckling theory to dictate just actually when it was going to buckle. And as we got up to a 12-foot truss, we found out that buckling became a major issue. So switching over to the Pratt truss, we were able to keep it in tension. Our sections. So the diagonals, even though they're in tension, the diagonals forces that we had to deal with were lower than the top and the bottom chord forces. And we found out that our bottom and top chords would have to be 10 by 10s. And when we moved into connections, we found out that if we tried to make our diagonals or our verticals 10 inches wide, then the members would be extremely thin. And we believe that actually the aesthetics of it and people crossing the bridge would then really start to ask questions, why are they so thin? So the way that we tackled this problem is we decided to get planks that were 10 inches wide by 3 inches deep, and then we would nail those together to create hollow sections. And that is how we solved the issue. And this also gave us another advantage by decreasing the dead load that was applied to our bridge. And lastly, the last major issue that we had to deal with the bridge was we attempted to make all of our connections for the lower and the upper chords, the diagonals, the horizontals, and the transverse beams at every node of the truss. And we found out that the forces were so great in the upper and the lower chords that we would need 2 rows of bolts, or else our rows would get so long that they would go past the node and into the other member. So the way that we solved this, and the reason why this is a major concern goes back to the expansion and contraction that I was talking about actually earlier. If you put 2 rows of bolts and then you put a gusset plate on the outside and you restrict the ability for the wood to expand and contract, it will then cause cracking that is parallel to the grains. So our fix to that, as you can see, is instead of making our lower and upper chords at the nodes, we then chose to make longer sections, and we would connect in the middle of the bays at 6 different connections. And at this point in time, it made it to where when we were connecting at the nodes, we then were able to connect the diagonals and the horizontals.
So alongside the design of the superstructure, we also completed a deck design for our bridge. As we mentioned earlier, we were designing for bike and pedestrian loads because of the constraint that we didn't have to accommodate vehicles or equestrian loads on the trail. So we designed for live and dead loads on the deck. We ended up with a design where the deck boards were transverse to the traffic because with our initial design constraints, initially trying to design for that vehicular load, we couldn't place the boards longitudinally because the span was too big and we would have to get really, really deep board members. So we have 2 by 12 deck boards placed transversely to the length of the bridge. These will be in southern pine because this is a very common decking material that you could pick up at any home improvement store such as Lowe's or Home Depot. This would make it really easy to replace out deck boards later if they were to start to warp or rot on the bridge. And then longitudinally, we have 4 6 by 10 stringers. These will be in beech birch hickory to keep consistent with the rest of the truss design. We also completed an approach ramp design for each side because we have to get up to the bridge somehow from the trails. Our west approach ramp is about 80 feet long, and both approach ramps follow ADA constraints so that somebody can easily get a wheelchair up onto our bridge. So the 80-foot long ramp is on a 1-on-20 slope so that we don't have to put any landing ramps in the middle. And then the east approach ramp is about 95 feet long. It includes 2 5-foot landing pads so that people can stop in the middle, and the slope on this is 1-on-12. We increased our distance between the supports to 10 feet, but we kept the same deck design for continuity across the bridge. The first support design that we proposed for the approach ramps is a moment frame style connection. So this will be installed similar to fence posts, where you dig a big hole and fill it with concrete and sink the post inside of there. We ended up needing 8 by 8 columns for this design, but our recommendation instead is to do a braced frame. This is our recommended alternate because it was much easier to pull out pieces and replace them if something were to happen during the lifetime of the structure. So with this braced frame, we have 8 by 8 columns again. This was for ease of connections because the cross brace on top of them ended up needing to be an 8 by 12 member to handle the forces from the deck. And then on either side, we have 2 by 4 cross braces to take that lateral wind load.
For our ramp foundation design, we used 15-inch diameter foundations going to a depth of 4 feet. We went 4 feet to get below our frost depth in western Pennsylvania and to also get below our scour depth. To connect our 8 by 8 timber, we're going to use angle, and then we're going to bolt it into the timber and also into the foundation. For our geotechnical investigation, we did soil sampling, soil testing, so we could proceed with the design of our foundations and abutments. We were unable to obtain soil borings, so we conducted 2 soil pits. One was on the west pit, and one was on the east pit. Our logs show that on the east pit, we went approximately 4.5 feet, with the top 4 feet being primarily sand and gravel, and then the next, the remainder was brown clay. For the west test pit, we went 5 feet in depth, and that whole length was all sand and gravel.
All right, so after that, we had to do our soil testing. Some of this was performed by us, and some was outsourced to Dr. Bunger's soil mechanics lab. Our first test was the sieve analysis. This gave us what percent of the material was what size. It also allowed us to classify the soil. The second test we performed were the Atterberg limits test. This lets you know at what water content how the material behaves. Third was a consolidation test. This gave us the total settlement of our foundations on each side of the bridge since our soil was different. And lastly, it was a triaxial test, which gave us cohesion and friction angle. These are both properties of the soil that control with bearing and overturning. So these are some of our results. First was the clay. The Atterberg limits, we found a liquid limit of 51%, as well, and a plastic limit of 42%, with a plasticity index of 9%, which is just the difference between the two. For the triaxial test, we found a cohesion of 2.9 psi and a friction angle of 27 degrees. For the sand, our Atterberg limits, we had liquid limit of 26% and a plastic limit of 0, which is normal for sand. In the triaxial test, we found a cohesion of 0, which is also normal for sand, and a friction angle of 34 degrees. So this was our consolidation test. We went with a loading of 2.5 pounds, 5 pounds, and then 7.5 pounds. Each of these loads were on there for a day, which allowed for settlement or consolidation. And in the clay, we found a total consolidation after 3 days of 0.052 inches. For the sand, we also went with the same loading of 2.5 pounds, 5 pounds, and 7.5 pounds. But with the sand, we found a total consolidation of 0.038 inches. These values will be used to determine the total settlement of our foundations.
Okay, so prior to our abutment design, we first had to verify our soil's integrity. And to do that, we would have to determine our bearing capacity and then consider a potential for overturning. So looking at the east side here, which we said earlier is primarily made up of clay, and there's the parameters that Dean went over just now. We built a bearing capacity analysis. We assumed the saturated soil, because this does fall into a floodplain, so there's a possibility for that. We set our test load at 115 kips, which is a little bit above our actual design load. And we came up with a minimum area of 4 foot by 4 foot, and that's at a depth of 5 foot. That puts us below our frost layer for Western Pennsylvania, and we came up with a bearing capacity for the east side of 7,000 pounds per square foot. And same deal with the west side, which is primarily made up of sand. Ran the bearing capacity analysis the same way, fully saturated soil conditions. The same test load of 115 kips. We came up with a minimum area of 3 3/4 foot by 3 3/4 foot area, and that's also at a depth of 5 foot. And for the west side, we got a bearing capacity of 6,500 pounds per square foot. Now, the minimum dimensions from the bearing capacity weren't sufficient enough to avoid the overturning, since bearing capacity only considers a vertical load. So we needed to consider the effects of moment on our abutments. So what we were trying to do was avoid any areas of tension. Soil can't take tension. So as you see in the figure up above, we just illustrated that to show if there are areas of tension in the pressure distribution diagram, you're going to have separation of the soil from the foundation. So to alleviate that, we needed to increase the size of our bearing area. We needed a positive pressure distribution throughout the entire footing. So we increased our final bearing area to 6 foot by 5 foot, and that gave us positive pressures at max 7,000 pounds per square foot and a minimum of about 170 pounds per square foot.
Now that we have our soil characteristics, we can move on to our abutment design. For our abutments material specifications, we used ACI 31814. For our concrete, we chose compressive strength of 4,500 psi, and steel reinforcement, we chose ASTM A615 grade 60 with a yield strength of 60,000 psi. For the cap design, we used a strut and tie model. The strut and tie model turns your beam into a simple truss for analysis. We used the ties in the place of where your rebar is going to be, or your reinforcement, so you can determine your tension strength. And your struts go where your compressive to connect your ties together. We determined from our analysis that our tension area, we needed to carry a load of 177 kips through our steel reinforcement. Our final dimensions of our cap are going to be 15 inches by 18 inches by 10 feet. For the cap detail, we used 5 number 7 hooked bars for the length of the tension zone, which is on the top of our beam. And then to counteract the shear, we used number 4 ties on each end at 2 1/4 inch spacing for the development length of our bar, and then at 10 inch spacing for the remainder of the beam.
So just to get into the column design, we had some initial design considerations. First, we wanted to determine the minimum dimensions that we needed, that required for the maximum axial load applied to the column, using the ACI code you see there. And then we would have to adjust those dimensions to account for any buckling that may occur. And then finally, consider our maximum moment. So this is our final design for our column. We came up with a square column, dimensions 18 by 18 inches. That's a 9 foot 3 inch tall column. Those dimensions there are well sufficient for our buckling. We wanted to keep our area of steel to our gross area ratio between 1% and 2% for an optimal design. So we set it at 1.5%, ran it through the calculation. We actually got a maximum axial load of 832 kip, which is way above what we needed it for. So we have a factor of safety of 8. I'm going to go ahead and say that's all right. So if you look to your right, there's a square. We have a cut cross section of the square column. We have the 6 number 8 bar, which we have situated as you see, and those are all tied together with number 4 tie bar at 16 inch maximum on center. And to tie in the footing and the cap, we went into the rebar tie-ins here. So we just needed to determine our development length, the extension length, and the bending radius. If you go back real quick, so the tops and bottoms are actually designed with the same specifications, with the exception of the bottom, which has a 30-inch lap splice to tie the column into the foundation pad. And basically from the foundation pad, we just need a skeleton of 44 inches to tie into the rebar cage for the column.
Okay, so after we had determined the dimensions of the column and the footing itself from bearing capacity and overturning, we then had to make sure that the footing was okay at those dimensions. So some of the criteria that we considered was one-way shear, two-way shear, moment, as well as moment and combined shear. The pictures on the right are the critical perimeters for one-way shear and two-way shear. So we were concerned with two-way shear at first. What that is essentially the column punching through the bottom of the footing. We had to also choose initial thickness. We chose 18 inches for that. For our final design, we went with a thickness of 18 inches and length of 6 feet and width of 6 feet, which was enough to satisfy the bearing capacity. And we went with a material, 10 number 5 bars longitudinally and 8 number 5 bars transversely. To determine that area of steel, we used the moment and found that that actually didn't control. What controlled was the area of steel minimum required by the ACI manual. So this is our footing detail in the longitudinal direction. You see the 10 number 5 bars. What I hadn't mentioned before was the temperature and shrinkage steel on the top of the footing, which was to prevent cracking due to temperature change. You can also see the column, as Dustin had mentioned, tying into our footing. And we use number 4 tie bars. This is the transverse section. Once again, you see the column tying in, the 8 number 5 bars, as well as the temperature and shrinkage steel again, and the number 4 ties, with a 3-inch clear cover all around.
After the completion of all of our designs, we put together an engineering estimate just to give Hollow Oak an approximate cost of what this project would run them when they're going and applying for grants. So you can see on the screen our comparison of alternates for the superstructure. The timber structure is about $372,000. The steel is about $373,000, and the fiber reinforced polymers are about $520,000. This would then get added to the cost of the substructure, which is about $29,000. The decking and the approaches, which come out to about $81,000. The total cost is listed at the bottom of the screen. Our recommended alternate, due to the reasons that were mentioned earlier and will be reiterated in a minute, our recommended alternate is timber at a cost of $482,000. These numbers probably seem high to some of the people out in the audience, just for our construction of our alternates. The reason that they are a little bit higher is that we recognize that the volunteer labor will not cost Hollow Oak anything as far as physical money, but we felt it was important to include an approximate cost per man hour to create a good comparison of the alternates. So in this, our estimate is about 10,000 man hours for volunteer labor for the FRP structure, about 12,000 man hours for the timber structure, and about 14,000 man hours for the steel structure.
So we would like to talk about constructability. And constructability from our group's perspective came from 30 plus years of actual construction experience. Actually 18 years from myself as being a bridge builder in the U.S. Army with 2 deployments, and with Dustin Volsky having 15 years as a card-carrying member just in the Boilermakers. And we believe that the most efficient way to erect this structure is to build it on the ground or in a shop and have it hauled in and then actually lifted into place. So finally, I'd like to cover our just our actual recommendations. Our recommendation came from the owner asking us to design a pedestrian bridge for their land trust. And we had access to actually the initial cost estimate that they were given from a different company. And the suggestion is the fire reinforced bridge that company provided could be built with volunteer labor. After the investigation that we provided, we have come to the conclusion that due to safety, time, and complexity of the project, that volunteer labor is not a viable solution for the construction of this bridge. And using those ideas, we have decided that a timber bridge is the proper design due to the lower cost compared to steel and the FRP, and also due to just the aesthetics. The aesthetics would be extremely important to an owner, in our opinion, because of the conservation idea. Our bridge would blend into the natural surroundings and would not be as much of an eyesore. At this time, I would like to thank Sean Brady, the owner, for giving us the opportunity for our first design experience to produce a bridge. We would like to thank the faculty of the University of Pittsburgh for providing such an outstanding education. And at this time, I would like to open the floor up to questions.
I'll start. I like this one very much because it's structural. I'm a structural engineer for about 50 years. And I very much impressed with feelings, especially the FRP presentation was very good because I use the FRP. Unfortunately, it is not good for this kind of applications for various reasons. Number one, you mentioned the fact that connections are almost impossible. But you did not mention another very important factor, deflection. Because the marginal elasticity of the FRP is so low. Steel is 30,000 psi, and this is probably less than 1 million. And that was very impressive. In the steel design, I wish you use T-sections for the top course and bottom course rather than the double angles for the ease of connections. And a lot of people today, double angles are the most convenient ways of building trusses. But there is one major disadvantage. You cannot paint them. Steel needs paint and maintenance. a gusset plate in between two angles. You cannot go in between splitting back-to-back angles. And especially, even with the sandblasting, they don't make tools fine enough to go in between those angles. So you have to also consider that effect, but I wish, because of that reason and other reasons, you should use T-section for the top bolts and bottom bolts. That's basically industrial practice. You go to professional like we will see, that you will never use two angles, double angles for the top bolt and the bottom bolt. And I was not very much impressed with the final decision the client made to make it from wood. And I think there are a lot of reasons for that for me to talk about, but I'm not, because probably I'm a little more biased than this. And there was one drawing in the, I think it was the cap design in color. Take a look at where the maximum shear is and see whether you are going to change your decision about where this stops. If you look at your front line this thing, your storms are very close at the X. That's where the shear is almost nothing. And then just take a look at it.
We had actually gotten that out of the ASCI code, or I'm sorry, the ACI code for the development length for the ties.
I'm not talking about that. Look at your cap, you have ties for all those ties. Look at the spacing of it.
Okay.
They are very close at the ends. They should be closer in the middle where the maximum shear is, because they close on full shear. Okay. And thank you very much. This side.
Dr. I.
That was one of the best presentations and projects I've seen, so congratulations. Just one comment about wood. Did you think about staining it afterward, because that might help preserve it? Didn't see that process.
We do understand that, as in with wood decks on houses, they have to be taken care of painted about every 3 years, that there would be some actual maintenance that we would need to take the time to actually look into. We didn't look into it far enough, but that is where we would continue to look. Dr. Bunger?
Yeah, can you guys give us a little bit of a background into your, you mentioned briefly sustainability in a couple of areas that jumped in and out, just as a word. Can you sort of flesh out how you were evaluating sustainability and how you were defining it in your discussions, what role that ended up playing in the end? Because, for example, you mentioned wood is more sustainable than steel is sort of an obvious fact. However, that could be quite dependent upon the source of the timber, right?
So we didn't do a very in-depth study into the sustainability. The design criteria for just doing the structural design took a large portion of our time. However, when looking through some brief information, looking online and looking through some of the sources that were provided during my sustainability class, actually, we were able to use the information given through that class and through the producer of the FRP to be able to give a rough estimate, obviously not trying to come up with any large numbers, but the steel manufacturing process ends up using a lot of coal burning, a lot of emissions to the environment, a lot of energy draw to be able to make the steel into what it's
Okay, so when
supposed
you
to
said a
be.
rough estimate, there was a blank there. That's a rough estimate of,
A rough estimate of the impacts that using steel, wood, or the plastic are going to have on the environment from a manufacturing standpoint, not for how it's going to impact at the bridge site.
Next question? Do we have one on this side of the room?
Yeah, so I'm Sean Brady of Hollow Oak Land Trust. I'm really grateful for this project. We build a lot of trails in the woods. $250,000, $500,000 bridge is a kind of a big step for us, and really appreciate the design and thought that went into this project. But the final recommendation, you know, 500,000 or so, is a lot for a bridge. So that's kind of the focus I'll be looking at, is how do we trim that down. But thank you.
I just want to know, like, it's hard to predict how much traffic this bridge will see, but did you guys consider that at all? Like, how many people do you think would use this bridge today?
I mean, the Montour Trail is a pretty widely used bike trail, so we don't really have an estimate as to how much this particular bridge will see, but hopefully increasing the access between the two trails.
It could be 100 or 200 people a day.
Okay,
Something like
that's more than I thought. So.
that. Montour Trail is hugely popular.
Yeah.
Do we have any more questions? Dr. Van Bush.
Some of you were looking primarily at people loads, but how will they, I assume this is a year-round trail and they have snow removal and is it wide enough to do that with a pickup, or I don't know how that's typically performed on this trail, was that considered?
Yeah, so basically, we're just gonna keep bollards at at each side, so this is not to handle any type of vehicular loading or equestrian loading. So as far as snow removal, maybe a shovel.
We did ask in the beginning of this project about the snow removal. And being that they have 10 miles of trails out there on this, they do not see it feasible to clear all their trails. So at that point in time, they don't feel they would actually uncover their bridge. It would open up access to trails that aren't groomed or covered. So they don't see a need to actually clear the snow off their trails. So they don't see a need to remove the snow off the bridge.
Covered?
Say what?
Was the timber option covered? I don't remember. I saw a picture of it, right? It was a covered timber option.
No, it wasn't. We had originally thought about it, that it would be anything to do in the beginning, but we did not get that far.
Good, thanks.
Question over there. You had mentioned some initial investigation into constructability and the different methods for constructing prefabrication and crane erecting, setting it in place. Was there an analysis done on the cost to prefabricate versus stick build in place, and then the additional shoring may be necessary to construct that, and then look at an overall construction duration when you factored that into the cost?
No, there wasn't. What we have at this point in time is just use a concept idea off of the multiple years of experience that we have ourselves.
So the costs are really more in the materials themselves that you've got quantified?
The cost quantified in our total cost up here also includes like an estimate of $25 per hour for the volunteers' time, just to place a value on that, because we recognize that it will take a lot of time and or a lot of volunteers. So the total costs aren't total monetary costs per se, but we will include in our final report a breakdown of where all this is coming from.
Any more questions?
It's lunchtime, just say that.
All right. Good job, team. Go team.